Let's tackle B. B looks a little scary at the beginning because you're almost like, oh no, quotient rule. But then when you slow down and think about it, there's just a 2 in the denominator, which is really the same thing as saying g of x is equal to 1/2 times all of this. So don't quotient rule things when you don't need to, right? We only need to do that if it's a function divided by another function, and we can't just like algebraically work our way out of it. Okay, so we have continuity because again, we're in just polynomial land. We have a closed interval. We have endpoints with the hard brackets. Cool. And now we need to actually take a derivative. And we have options. If you are pro algebra, anti-chain rule, you can go ahead and distribute out that x squared minus 1 squared, right? Or if you are anti-algebra, pro chain rule, we can just do the chain rule. So I'm going to go ahead and chain rule this just because I love a little bit of review. So in order to take my g prime, which I'm doing to find my critical values to do the candidates test, I'm going to set the 1/2 is just a scalar multiple, so I can just leave that out there. We're going to apply the power, so this will be times 2 x squared minus 1. This is a chain, right? What's inside of that is a little different. And we've got times 2x, which is of this inside function, right? And the 1 looks prime, so I'm gonna get rid of that. So, okay, we can clean this up a little bit before we go set this equal to 0. Again, not going to be undefined because we're in polynomial land. The 2 and the 1/2, bye. We have an x squared minus 1 times the 2x. And we can set this all equal to 0 and our critical values, which means either x is equal to minus 1, your choice. You can factor that different squares, or you can go ahead and solve x squared minus 1 is equal to 0, but you should have plus or minus 1, and x is equal to 0. So candidates here, right? -1, +1, and 0 are all on our interval. So we go to set up this table, which I'm running out of room for. I'm going to have -3, -1, 0, 1, and 2. Now, don't get fancy here. I saw some students previously just try every freaking value discretely. It's a bad idea. I want to see you doing the candidates test. If you don't do the candidates test, you're getting an almost on this problem, right? And then we need to figure out what each of these things are in the original. Oops, I put f of x, but it's a g of x. In the original function, not our derivative. All right, so -3 squared is 9. Oh, I'm already hating life. -3 squared is 9. +9 minus 1 is 8. 64 divided by 2, this is 32. All right. 1 minus 1 is 0. Whew, thank you. 0 minus 1 is -1. Squared is a +1. Cool. 1 minus 1 is still 0. And we have 4 minus 1, that's 3, 9/2. Okay. So we've got our absolute maximum and we've got our absolute minimum, which happens at two different values of x. So absolute min is 0 at x is equal to plus or minus 1, being really lazy there. And absolute max is 32 at x is equal to -3. And it's been a hot minute since I checked Desmos, and I did a lot of mental math there, which you guys know is not my jam. So let me go ahead and just toss this one in so we can see. We have an x squared, get out of here, x squared minus 1, all squared, all divided by 2. Okay, looks like there we go. Our two minimum values were at -1 and 0. Let me go ahead and do one more thing here. Let me go ahead and add in that limitations, -3x 2. So we can see it truncate. So there we go. Hide this. Come over here. My endpoint here, I can't get there. My endpoint is undefined because I didn't put an equal sign, but that you can see where it's going. All right, my kid is home, so we're done.